Welcome to the second unit in week 6 of the Parallel Programming Concepts course. After we saw some ideas about parallel design patterns and how parallel programming can be guided by design patterns and best practices collected by other authors, we now want to have a look into one particular methodology for the development of parallel software. And this is what we call Foster's methodology. The author of this methodology is Ian Foster, and he wrote a book which is comparatively old, Designing and Building Parallel Programs. Ian Foster is a well-known professor in computer science who works in the area of grid and cloud computing and in highly scalable parallel systems. And he summarized a lot of findings and best practices in high-performance computing in this particular book. And one part of this book is a methodology to approach a parallelization problem. So in contrast to the design pattern collection idea, where we have different templates of solving issues, this is more like a guide through a particular parallelization project. So what are the steps you can take? The methodology has a tendency towards shared nothing systems, MPI-based applications, but whenever the word communication is used in here, then this relates to messaging, but you could also translate this to synchronization in a shared memory system. So the methodology should be overall applicable to different parallelization problems. What is the proposal? The proposal here is to define 4 distinct stages in the attempt to parallelize a particular problem. The first phase, the first 2 parts, are the search for concurrency and scalability. So this is very similar to what we saw with the Metzen idea of design spaces. And the second part is the search for locality and performance. So in Foster's methodology, we start with the partitioning step. And the partitioning step is the phase where we take our problem and try to split it up into very fine-grained tasks and concurrent activities. So this seems to be a common idea between all the different authors, that when you start, the first thing you have to do is to find concurrency, either based on data or on tasks, so that you get a lot of small parallel potential tasks inside your problem definition. The second step after the partitioning is then the communication step. So as I said, in shared memory systems, you could replace this or interpret this as synchronization or shared data step. And in this part, you define necessary communication or data exchange between your tasks. So after you first defined a lot of different small tasks, you now talk about the question, how do they communicate? How do they interact? What are interdependencies, data dependencies, for example? What are data flows between the activities? And you somehow write that down or note for yourself, for example, in a graph model, in order to get a bit better feeling for how your parallelization approach would look like when you put this into practice. When you have this idea of different concurrent activities, fine-grained tasks, and communication, you go into the next phase, where you search first for locality, and this is called agglomeration. So now you take your different fine-grained tasks and put them together again into groups. We saw this task grouping also in the Metzen approach in the last unit, where it was at an earlier point in time. In Foster's methodology, the idea is to do the grouping comparatively late. So first you focus on finding all the exploitable concurrency, and then after you have it, you start to re-agglomerate again in order to avoid performance bottlenecks or a too fine-grained communication. And then in the fourth step, you do the mapping. So you take your resulting task graph with communication and task groups and put it on a particular infrastructure. And if you do that, you need to match task groups on execution environment, nodes, or processing elements. And this is the mapping problem you also have to solve in the parallelization. So let's get through the different steps again. This is an excerpt from the book, so you can also read it in the original literature. The first step is the partitioning step. And the main interesting point here is, do you want to aim for data partitioning or computation partitioning? This is sometimes also called data parallelism and task parallelism. And the idea is always that we either take the data being processed and slice it up and define parallel activities, concurrent tasks for each of the data items, or we have different computational activities. And this would be computation partitioning or task partitioning. So each of our different tasks and processing attempts are defined as a separate, concurrent, hopefully parallel activity. The point here is that you need to take your algorithm or your computational problem and you need to reveal the hidden structures. So you need to take different viewpoints on the problem. This may, again, demand some kind of backtracking where you go back to an earlier step if you figure out that this partitioning scheme doesn't really work. In this phase, it's especially important that you try not to replicate data or computation. This is a well-known optimization strategy for performance, but it's not very valid at this point. So here we only want to find the concurrency, and in many cases you will have multiple candidate solutions. Either we partition our problem like this or that. Decomposition types, as I said, are either domain decomposition or database decomposition or functional decomposition. These are again alternative terms for data and task parallelism at the end. You see here two examples from the Foster book. You either have three-dimensional data cubes where you can now decide if you want to cut it into rows or in columns or in little tiny blocks. With functional decomposition, you typically have some kind of scenario for your problem. For example, here the picture tries to represent a simulation, a weather simulation scenario where we have an ocean model and an atmospheric model. And it is tempting now to say that we do a functional decomposition based on the different models because they can in themselves compute their own results and afterwards exchange them. So when you do the partitioning, Foster proposes a particular checklist, which is very helpful, that helps you in identifying if your partitioning is a good one or a bad one. So the first thing you have to make sure is that you have at least an order of magnitude more tasks than potential processors in whatever hardware you may aim for. This is relevant so that you have some flexibility for the next steps because we want to do the later agglomeration. So we need enough potentially concurrent tasks in our initial definition in order to have something to group together. Do you avoid redundancy in this point? So do you have really an efficient partitioning here? And do you have tasks of comparable size? This is also very important. When you want to have a later performance optimization, it is very helpful to define task granularities that are equal so that it's easier to combine them and to scale them to a particular execution environment. And you do these checks, and if you figure out, oh no, this doesn't look good, I have very unbalanced load here, big tasks and small tasks, or something like this, then you go back and try another partitioning strategy until you get something that looks satisfying and worthwhile the next step. The next step then is the thinking about communication. So you define the notion of data consumers and data producers. Who is sending data to whom? This is not necessarily message passing. It's really about the data flow inside of your problem. Who's giving what to another function? Are there maybe real dependencies where a particular task can only work if he gets the result from an earlier task? Data dependencies are often tricky to handle, so it's very complicated to deal with them in the real implementation. So it's a very good idea to do the thinking about them on an abstract level. As I said, graph notations are very helpful here so that you can get a better look on where are my communication clusters, where there's a lot of data exchange going on between the different parallel tasks, and where I have only a few links, which gives me, for example, the chance in a hybrid environment to put these partial loads on different machines in a cluster. Communication patterns or data exchange patterns in such a graph can be categorized. You either have local or global communication. Obviously, local communication with only a few neighbor tasks is a good thing because global communication is hard to scale when you want to add more execution resources. You may have structured or unstructured communication. Structured communication is a good thing because this is easily mappable to a particular interconnection network. So if you have, for example, a tree structure inside your application and you have some kind of torus interconnect in your cluster, then there are well-known approaches to map one thing on the other. So having a structured communication inside your algorithm is a thing that could be an advantage for your later scalability. Static versus dynamic communication structure, remember CSP channels versus actor communication. A static communication is good because it's predictable. The graph, the communication graph is not changing, so you can plan better for some kind of grouping or some kind of performance improvement. While with dynamic communication, you don't really know what's going on at runtime. You cannot really think about this beforehand, which makes it a little bit harder to achieve a real speed up and scale up in your application. And then synchronous and asynchronous communication. And this is more like an implementation detail than a particular algorithmic property, but you may also think about that at this part. Checklist for communication design. The overall point should be that you're not producing bottlenecks, central managers, tasks that have to communicate with all the others. The best way would be to have tasks that more or less equally have the same amount of communication, or they only have local communication. And you should try to make sure that computation and communication are hopefully able to be overlapped so that you can do these things at the same time. This depends a little bit on what kind of computational problem you're facing. When we take the bubble sort example again, then the point really is there that you have independent access to data, so there is no synchronization need between the two parallel activities. This is a good thing. This is the perfect way to do it. Okay. One particular strategy that turns up often in this part of the design is the idea of ghost cells. This is just to give you one hint of possible precise design patterns that may be used in the communication part. Ghost cells is the idea that you have separate tasks dealing with their own local data set, and at some point in time they need tasks from the other one mutually. And the question is now, how do you deal with that in your algorithm? One way would be to simply copy the data you need from the other task in the moment where you need it. The other idea would be to access it remotely, for example, sending an MPI message and asking for it, or using more advanced techniques like RDMA. So there are different ways of dealing with it, and ghost cells is the idea of formulating your algorithm in a way that the remote data structure you want to use is handled as it would be your own. So internally in the structuring of your algorithm, you act like you have more local data, but the truth is it's only filled and accessed and fetched in the moment where you need it. And this delays communication to a later point in time, because instead of copying it explicitly as part of your algorithm, you just delay the communication attempt to the point where the computation needs the remote data. And that's the idea of ghost cells. This is one example of how to deal with the different communication variations you may aim for, you may see in your algorithm. The third step is agglomeration. So after we now have a good, well-structured, hopefully balanced communication graph with a lot of local communication, we now turn to the particular execution environment. So in the agglomeration phase, this is the first time where we say, okay, we are aiming for GPUs, or we are aiming for shared memory SMP systems, or we are aiming for a shared nothing system. So we choose a particular system, we look into it, and we figure out, okay, we have this number of execution units, we have this communication behavior. LogP is, for example, an interesting approach to describe the performance of the communication channels. So you get an understanding of how your execution environment looks like, and now you recheck your partitioning and your communication decisions, and you start to think about, okay, if I have this communication graph with these tasks, does that really work? And if you did your partitioning right, you should have the situation that you have way more tasks than processing elements. So how do you deal with that? You group them. You take the tasks, you put them together on one processing element, and either they have some additional kind of low-level parallelisms, such as ILP mechanisms, or you just have a concurrent execution of them on the particular node. But since you have now the consideration of both task granularity and communication amount, you can really make sure that task groups that have only a few communication links are put on different nodes, while tasks which have strong communication links, a lot of data exchange going on, are placed on the same node, for example, to benefit from a shared memory system. So you see here the agglomeration step is clearly more targeted towards shared nothing environments, but when you think about large-scale NUMA systems, this may also become there. The problem with the agglomeration step is that you have conflicting design decisions or conflicting guiding decisions. On the one hand, you want to have coarser granularity in order to reduce communication. On the other hand, you still want to have several parallel activities to be able to have a flexible mapping later. If you only have two big chunks of of task groups, and you want to put them on the execution environment, you have no real choices anymore. So this is a balancing act. And the third conflicting guiding decision is that you don't have endless time. So at some point in time, you need to decide for a solution. When we take the agglomeration problem, then it turns out that this is what we used to call the granularity issue, the task granularity issue. We already talked about the surface to volume effect in week 5. And this is basically, again, the idea of surface to volume. So we need to decide, we need to balance between coarse granularity, which reduces the communication overhead, and fine granularity, where we have better chances to exploit existing parallelism in the hardware. And this must be done according to a particular execution environment. So this can't be done in an abstract way. Therefore, it's step number 3. You can only do that if you know what kind of execution environment you're targeting. The next good thing about this methodology is if you're exchanging the execution environment, so you're going, for example, from GPU to cluster, which is completely different, then the first 2 steps and their results are still valid. So you hopefully can reuse your existing idea of concurrency and parallel tasks in your application, and now just repeat the agglomeration and the later mapping step with respect to your new execution environment. So Foster's methodology, if done right, can help you in reusing your old analysis results for your parallelization attempt. Checklist for the agglomeration is, do we really have the granularity effect? So if we increase locality, if we make coarser grained tasks, do we really get reduced communication? When we do replicated computation, so we could, for example, instead of communicating and exchanging data, we could replicate some computation. Does this outweigh the costs? So a typical approach that works in GPUs, such as replicated computation, may not be feasible for another execution environment. And this is a decision we have to make here. Does the number of tasks still scale? So if we increase the problem size, thinking in Gustafson's law, does this give us still more tasks that are still balanced in the right way? Or do we need a better agglomeration with an increasing problem size? And so on. So you see a couple of questions here which all relate to the question, does our agglomeration, our task grouping match to what we see in the execution environment? And the last step in Foster's methodology, as we saw, is the mapping step. And historically, this was only relevant for shared nothing systems. So you have your cluster and your different nodes with the interconnect, and now you have to put agglomerated task groups on the particular cluster nodes. Then you have communication in between them, and the whole cluster is running your parallel application. From our thinking, Foster's methodology is also applicable in shared memory world, especially when you look into the recent trend of NUMA systems with deep memory hierarchies. Because when you take such a scenario, then, for example, also as we saw in PGAS languages, then we have the consideration of either local memory or global memory. Although local memory is just a special section of the global address space, it has better performance characteristics. So the point of agglomerating tasks and putting them on a NUMA node to make use of NUMA local memory, this is something that is also more and more relevant when you program parallel software for shared memory systems. So therefore, our proposal would be to take this methodology and also trying to attempt it in a shared memory world. When you do the mapping, what you basically want to do is we want to reduce the overhead, the communication overhead. So this is the serial fraction in Amdahl's law, which eats up the performance boost you get from the parallelization, and you want to get rid of it as much as you can. So try to put heavily communicating tasks on one node or on the same node, and take another task group and put it on another node so that you get the best possible overhead scenario in your parallelization attempt. When we take this mapping problem and try to ask the question, are there any kind of formulas or tools or algorithms that can help us in solving this problem. The interesting answer is that this is still a research problem. It relates to the so-called NP-complete problems, especially to bin packing. So here we have an interesting ongoing research topic in computer science, which is the question of how do you map a task graph, a communication task graph, on an execution environment graph, for example, cluster nodes and network interconnections. What is the best mapping? And this computational problem or this algorithmic problem is still investigated. There are a lot of good heuristics. So if you're interested in that, please check for task mapping in scientific literature and in the books, because this gives you more information about how this can be solved in a more automated fashion.